Hey guys, so today I will be explaining chapter 6 and basically summarizing what chapter 6 has. So, first of all, we're going to start with the formulas that chapter 6 includes and that we should know. So, the first thing, important thing we should know is summation notation and what it is. So, summation notation is basically this kind of like a weird kind of E right there. And so, this basically I guess shows you like what the number is on top or that k equals to 1 when limit n upwards to the infinity. And then over here it just shows the function and the absolute x over there. So now we're going to talk about the definite integral notation. So this one is mostly used when you are trying to, I guess, solve for f prime of x when solving definite integrals. And so there's an opposite way that they also do, which is this part. So if they give you this, you have to try solving it with this. So if example, the question was this, right? But like the numbers and stuff, and then it will show you to solve for f prime of x, and you would have to you would have to use this formula to solve it. So it's kind of like an opposite. They have opposites that you have to know how to do, so you can understand both ways on how to use the formulas. Now, the fundamental theorem of calculus is basically where you kind of, I guess, don't know how to explain it, but you use the chain rule and I guess find a way how to find f of x instead of f of t and dt by using those. Basically finding f prime, I guess you could say, but solving by the derivative or using chain rule or whatever the equation gives you that you need to find out on how to solve it. So there's another way that has more variations of FTC, which is fundamental theorem calculus. It's just a short form of that. And this one just shows you other formulas that you can use in order to find the answer. So this one has g of x and a ft times bt. You can solve it by using this formula. And then you can use by this formula also, where it has g prime of x minus f h of x and h prime. So, it has different ways you can solve it, and it depends on the question they give you. Like, if whatever fits the formula, use it so you can solve it easily and carefully. Now we have another fundamental theorem of calculus, but this one is mostly based on definite integrals, and it's kind of where f of x is basically the antiderivative of f, I guess you could say. So this is like solving antiderivative, which means antiderivative basically means where you solve before it. Like, for example, if there was a question or they give you like an equation, like for example, I'm so sorry, if they give you a question like f of equals to 2, then the antiderivative will be 2x, because 2x and then you do the derivative is equal to 2 because x is equal to 1, right? So it is equal to 2. So this is an example of antiderivative. You're just kind of going the opposite way instead of the way you usually go when solving for the derivative. So this is basically the first part of the formulas I'm going to be showing you. Okay, so this is a part 2 of the chapter 6 formulas, and this is the properties of definite integrals. There's a lot of ways you can solve it from solving. So the properties of definite integrals are basically formulas where you can solve by different variations that they include. So for example, the equivalent limits a and a on both top and bottom, f of x and dx equal to 0, because it doesn't make any sense. Even when you solve it and they give you example like 5 and 5 and they give you like an equation right here, when you solve it, it will still give you a 0 anyways, so easily it's just equal to 0. Reversal limits would be the reverse of that, so this is positive, so this would be negative by b over a, and you just solve it from there. Multiply by constant, it has the constant k right there, and you just solve it from there. Adjacent intervals, so this is basically where they have c now, so it's c. It's basically the interval would be like this, like that. So they have c over a, f of x dx plus b over c. Is that c, I think? Yeah, that should be C. And then you have B over A, which is basically that. So now we have addition. Addition is pretty important here. It's pretty common sense right here, since it's just adding right here, because it's addition right there. You just use it from the f of dx and g of x right there. Subtraction is basically the same thing except it's just subtraction, and this is basically the formulas you might use when solving equations that include using these formulas. Okay, so this is part 3 of the chapter 6 formulas, and we'll be talking about the trig. So this is kind of like a recap back from chapter 2, where we had to solve the derivative of the trig functions, but now we are going to solve them by the integrals. So sine and cosine integrals is sine of x dx equals to negative cosine x plus c. So this is mostly like antiderivatives mixed kind of ways how to solve, and then cosine x of dx would be sine x plus c. Exponential would be e to the x dx equals e to the x plus c, so the same thing, no change at all for exponential. But then for a to the x dx is a to the x over ln a plus c. So it's kind of like a fraction now instead of not a fraction. Logarithm will be 1 over x dx, and now it would be integral x over negative 1 dx equals to ln x plus c. So same thing, c will be the constant, so we have to include that. Trig integrals would be integral secant squared x dx equals tan x plus c. Cosecant x cotangent x dx equals to negative cosecant x plus c. Secant x tangent x dx equals secant x plus c. And then cosecant squared x dx equals to negative cotangent x plus c. Now the inverse trig is also included. So d over dx sine, and then inverse would be sine negative x plus c. Or you can say arc sine. One of those two is fine. Arc sine would be 1 over absolute x and then square root of x squared minus 1. Arc tangent x would be equals to 1 over 1 plus x squared. So this is basically the trig functions of antiderivatives and the integrals on on what formulas we have to use in order to solve integrals that has trig functions in it and inverse. Okay, so this is chapter 6. This is chapter 6, but this is lesson 6.1, and this is a 6.1 problem. So it says you are on a road trip and have your car on cruise control for 3 hours. You travel at 40 miles per hour. How far have you traveled? So cruise control is in 3 hours, but you travel at 40 miles per hour. So how far have you traveled? So here we have a graph. It says hours is right here and miles per hour is on the y area. So the line they already provided a line crossing through all the hours, but the only one that we need to think about is 3 hours only. So this is called area under the curve. So you basically find that does not mean it's under the curve, okay? It just means the under does not mean it's below. It just means it's between the x and the function. So here we have x and the function right here. So 3, let's make a line right here where 3 is, okay? And we basically have like a rectangle right here, right? So you just, if you want to shade it, you can shade it, but this is basically your area. You have area already. You already have it captured. So we already have that. So in order to solve this, we would have to solve from where? We have to solve from 40 miles per hour, right? Hour, okay? And then times by how many do we have? 3 hours or 1, okay? So this is basically the formula you would use in order to find it, okay? And this is equal to what? So 40 times 3 is 120, and you have 120 miles. So it's basically using the area of length times width, because rectangular area is equal to length times width, and you just use that over here. So 3 times 40, and then you just get your answer, and it's 120 miles. He has traveled 120 miles. Okay, so now we're going to be talking about approximate areas with Riemann sums, and basically this is they have 2 different ones, but there's actually 2 more, which is midpoint and trapezoidal sum. We're going to talk about we're going to talk about it after we solve these. So left Riemann sum is basically where example, if you want to go to left side, so you have 2 and 4 right here, right? Oh no, sorry, 2, 3, 4, 1. So basically you would, I guess, start at the left side. You see how this is the left side, and then you would just go like this. So this would be the left side. For the right Riemann sum, you have 1, 2, 3, 4 right here. So the right Riemann sum would be basically going over here. Okay, so this would be like this, this, and then this. And this is how you would solve left and right Riemann sum. Now for midpoint, it's kind of a little similar, but a little different. So as you see here, so let me just erase this part right here, okay? Let me just erase the left one. So example, you have this, correct? Or actually, let's do like a parabola. So example, if you have going from here to like 4, this is not a good parabola right here, but it's an example of it. So you would use the midpoint right here, or for example, if you want to solve between 2 and 3, you would find a midpoint right here, and then you would just solve it. You just make a line to solve the area. So for example, for trapezoidal, right, you would need a parabola or any kind of shape. I'll use parabola because it's much more easier to explain here. Trapezoidal would be like, for example, you have 4 right here, and you want to solve 4 and then use another one right here. So you would use, with trapezoidal would be like this. And same on the other side, be like this. This is trapezoidal, and you would find the area of 1 here and the area of 1 right here by using the trapezoidal formula, which is A1 plus, it's 1/2 plus, 1/2 times by B1 plus B2 times by H. And this is basically, you would solve area. Okay, so this is basically where you would write a summation notation equivalent to the definite integral. So remember when I showed you the formula between the summation notation equal to the definite integral, this is what we're going to be using for. So we have to use the summation notation formula, or basically, yeah. So it says the definite integral is 9 and 0, and then you have to find the square root of x times by dx. Okay, so the summation notation formula would be k equals to 1. Okay, and then we have, so 9 over 0. Okay, so that would be 9 over n. Because b minus a over n is equals basically to the absolute value. Not the absolute value. The derivative. So basically 9 minus 0 over n equals to 9 over n. So this is how I found 9 over n. And then it would be, and then you would use the square root to solve, because it's square root right here. So it would be 9 over nk. And this is basically the answer for this problem. Okay, so this is basically solving by the antiderivative formula. And so we have power over 2, 0, 6 sine fx dx. So this is basically using the formula, the antiderivative sine of x. So let's try solving it out right now. So we have 6 cosine because of the antiderivative, and then we have pi over 2 and 0 just to make sure with the interval here, and then it would be negative 6. I'm sorry guys. It would just be 6 actually, because there's no negative here. So it'd just be 6 cosine and then pi over 2 minus 6 cosine 0. You would basically substitute it because of both a, b, and a, and then it would equal to 0 plus 6, which would equal to 6. And this is basically your answer for this problem. Okay, so this is solving indefinite integrals. This is kind of like adding c into the constant, while the definite integrals was basically solving for f and for f prime of x, and then, you know. But this one is basically like finding the indefinite integrals right here. So we have integral 7 to the x dx. So if you think about it, the formula for ax dx was what? It was a to the x ln a. It was like that plus c, right? So we just have to do the same thing for 7 to the x. So it will be 7 to the x ln 7 plus c. And this is basically your answer for this problem. Okay, so this is solving accumulation functions, and basically we have to find f prime of x. I forgot to put that there, but you have to find f prime of x by solving this. So basically, accumulation functions is basically where I did include a formula about it. There are different ways you can solve it with FTC. FTC meaning fundamental theorem calculus, and there's many formulas you can use by solving these problems. But the most common formula I'll be using for this one would be with the constant. So this one has the similar formula for this one would be x over a f times by t, or d, well, I meant t, but because you see x is basically here and a is basically 0. So for this formula, the answer for this one would be this. It would be 10, or how you would solve would be this one. D over dt, and then x would equal to 1. So it's just equal to 10. And this is your answer for this problem.